Okay, so good afternoon all. So first of all, let me know whether audio and video everything clear. So first of all, let me know whether audio and video everything clear. Yes. Okay. Sivakumar, good evening Sivakumar. What you are asking, sir, you will provide notes or writing myself notes? See, if you write notes yourself by listening the lectures, it would be more effective here. Okay. See, I am already giving the lectures or not? Yes or no? So based on these lectures, you have to write your own notes. So each and everything I am writing on the board or not? Yes or no? Okay. So based on that, if you write notes on your own, so it is going to be very much better, right? Okay. Okay, yeah. Okay. So we are dealing with the subject electromagnetics. We are dealing with the subject electromagnetics. Right. Okay. So today we are going to start the topic that is magnetostatics here. We are going to start the topic that is magnetostatics. But before going to this topic here, so I would like to discuss one special case in case of potential and potential energy here. Actually, I thought to complete that special case yesterday itself, but I have forgot to explain that special case regarding electrostatic potential energy and electrostatic potential. Okay, so that special case will take maximum 15 to 20 minutes. So within 15 to 20 minutes we will complete that special case. Okay, so then after that we'll start magnetostatics here, right? Okay. Okay, yeah. So so I'm going to deal with a special case here. I'm going to deal with special cases. Okay, so that is this is for electrostatic potential energy and electrostatic potential. So if I complete this one, then electrostatic potential topic will be completed 100% here, right? Okay, so special cases. So just have some patience here for 15 to 20 minutes. So after that we will start magnetostatics, right? Okay. So in general we are going to consider, whenever we are dealing with electrostatic potential and electrostatic potential energy, in general we have considered the potential at any point is defined with respect to what? Is defined with respect to some other reference point, and in general that reference point will consider it as what? Infinity. Yes or no? Okay. So in general here, in general the potential at any point is defined with respect to some other reference point, with respect to some other reference point. So in general we have considered that reference point as infinity, and at infinity we considered we considered the reference potential, yes or no, we considered the reference potential as V infinity, which is equal to what, which is equal to 0, yes or no. So in general, the potential at any point is defined, must be defined with respect to what, must be defined with respect to any point. You can write here must, here you can write here must, okay. So any point must be defined with respect to some other reference point. So in general, we have considered that reference point as what here, infinity, and at infinity we considered the reference potential. This is reference potential here, reference potential as V infinity, which is equal to what, which is equal to 0. So here what we have done here is if suppose for example, okay, so I have considered a charge capital Q here, okay. So here I have considered another charge Q. So whenever I am writing the distance from here to here is R. So whenever I am writing the potential at R here, so how I have written here, the potential at R with respect to what, with respect to some reference. So what is that reference? That is nothing but infinity. So in this manner I have written. So VR infinity is equal to what, is equal to, so Q by what, don't take this small q here, okay. So just I am writing the potential, right. So the potential at this point R due to this capital Q, so that is equal to Q by what, Q by 4 pi epsilon naught into R, okay. So if the medium changes, then this epsilon value is going to change here, right. So VR infinity means VR minus V infinity, which is equal to what, which is equal to Q by 4 pi epsilon naught R. So therefore VR is equal to what here, VR is equal to Q by 4 pi epsilon naught R plus what, plus V infinity, plus V infinity, yes or no, okay. So this is the potential at R, this is the potential at R with respect to what, with respect to infinity. So this is going to give you, the gain in potential, at R with respect to what, with respect to infinity, understood. And here we have considered in general the potential at infinity here, in general the potential at infinity we have considered as what, we have considered as 0. Okay, so we know this potential here, we know this potential at infinity, so that we have considered as what, infinity, so we have considered as 0, right. So this is how we have solved the problems, right. Now if suppose it is not compulsory that always you have to take the reference point as infinity, okay. So in general if suppose if they have not mentioned anything, so you can generally take the reference point as infinity. If suppose in the problems they have given like this here, suppose in the problems they have given like this, so let us assume, okay, so let us say they have given like this, okay. So let us say they have, so let us say they have given in the problem, let us say they have given in the problem to consider or to take, or in the problem to take the reference point, as some k, to take the reference point at k such that, or I can say at k, okay, so where k is not equal to infinity, understood. So let us say they have given in the problem to take the reference point at k where k is not equal to infinity. So in this manner they have given here. So in this case how to write the potential at R, So now they are saying that you have to take the reference point at k where k is not equal to infinity. So in this case how to write the potential here? So now the potential at R here, okay. So the potential at R, now the reference point you have to consider as what? You have to consider as k. So the potential at R with respect to what? With respect to k. The potential at R with respect to k. So that means as you move the unit positive charge from point k to R, what is the gain in potential? That's what it means. Okay. So now you are measuring the potential at R with respect to K. Now the reference point they have specifically mentioned to take the reference point as K. So in that case you have to write the potential at R with respect to what? With respect to K. So that is I can represent it as what? VRK. So now in this case VRK is equal to what? So in this case VRK is equal to Q by what? The potential at this location is nothing but Q by 4 pi epsilon naught into R. Now here VR minus VK is equal to what? Is equal to Q by 4 pi epsilon naught R. Now here VR is equal to what here? VR is equal to Q by 4 pi epsilon naught into R plus what? Plus VK. Okay, so what is the gain in potential at R with respect to K? With respect to K. Understood? Now you have to consider the reference potential at what? Reference potential at K. Understood? Okay, so this is a special case here. This is the special case. So that means if they have not mentioned, if they have given in the problem to take the reference point as some point K which is not equal to infinity, so in that case you have to consider the reference point at K. Understood? Okay, so if you consider the reference point at K, then the potential at R is equal to what? The potential at R is defined with respect to what? With respect to this reference point K. Understood? Okay, so now I will give you one problem here based on this, then it is going to be very much clear. Okay, in general if they are not considering the reference point at infinity, then they must mention the reference point. Okay, or they have to tell at least don't take the reference point as infinity, so you take the reference point other than infinity. So like that also they have to mention here. So if nothing is mentioned, is that is meaningless. Okay. Right. So if they have not mentioned anything, generally we will take the reference point as infinity, and at infinity we consider generally the potential as 0. Understood? Okay. So now see here. So suppose I have given a problem like this. Okay. So let us say a point charge Q, a point charge capital Q is placed at 0, 0, 0. Okay. Now I am considering a point B here. So which is 1 by 2, 0, 0, and point C here which is 1, 0, 0. Now here I am considering a point A. Let us say this is 2, 0, 0. Okay, so I have given the figure in this manner. Now I am saying that the potential at VB with respect to some reference point K. Now here take the reference point as K. Take the reference point as K where K is not equal to what? Where K is not equal to infinity. Okay, so you should that means they are specifically mentioned that to take the reference point as K where K is not equal to what? Where K is not equal to infinity. So that means you have to measure the potential at any point here. You have to measure the potential at any point with respect to what? With respect to this reference point. So that's what it means. Right. Okay. So in this case, the potential at B with wait. Okay, so let us say wait here. Okay, so here in this problem, so K is not equal to what? K is not equal to infinity. So this is what they have given, and they have said that the potential at B is potential at B is 30 volts. Potential at A is 15 volts. Okay, so then determine the potential at C. Okay, so this is the question they have given here. So here what they have mentioned here, they have said that here take the reference point as what? Take the reference point as K, where K is not equal to infinity, So potential at B they have given as 30 volts, potential at A they have given as 15 volts. Then they are asking to determine the potential at C. So in this case, how we can solve the problem here? See here. So first of all, you have to determine the potential at what? The potential at this reference point. Yes or no? Okay. How you can determine here? See here. So here the potential at any point is defined with respect to what? With respect to K. So the potential at A with respect to K is equal to what? Is equal to, so due to a point charge at A, so that is Q by 4 pi epsilon naught into what? Into the distance from here to here. What is the distance from here to here? Is nothing but 2 units. Okay. So therefore VA is equal to what here? VA is equal to Q by 4 pi epsilon naught into 2 plus what? Plus Vk. Why here? VA is nothing but what? VA is nothing but VA minus what? VA minus Vk. So I have sent Vk to that side. Okay. So this is nothing but VA here. This is nothing but VA. So let us consider this as what? This as equation 1. So next, similarly, the potential at B with respect to K. So that is equal to what? So what is the potential at B here? The potential at B due to this point charge capital Q is nothing but what? Is nothing but, we know that it is nothing but Q by 4 pi epsilon naught into what? Into 1 by 2. So therefore VB is equal to what here? VBK is nothing but VB minus Vk. So therefore VB is equal to what? I can write it as 2Q divided by what? 4 pi epsilon naught plus what? Plus Vk. So this equation I am considering as what here? I am considering as equation 2. Okay. Now from here, what I am doing here is, so I am doing 2 minus 1 here. So equation 2 minus equation 1. So what you are going to get here? VB minus VA. So VB minus VA. So is equal to what? Is equal to, so whenever you are subtracting VA from VB, this VK will get what? Will get cancelled. So what is left out here? 2Q by 4 pi epsilon naught minus what? Minus Q by 4 pi epsilon naught into 2. So from here you can take Q by 4 pi epsilon naught common, then what you are going to get? 2 minus 1 by 2. So 2 minus 1 by 2 is how much here? 4 minus 1, that is 3 by 2, that is 1.5. Yes or no? So you will get 1.5 into Q divided by what? Divided by 4 pi epsilon naught. So that is nothing but what? VB minus VA. So they have given the potential at B. The potential at B is 30 volts and the potential at A is what? A is 15 volts. Okay. So the potential at B is 30 volts and the potential at A is how much? 15 volts. Okay, so that is equal to 15 here. So 15 is equal to 1.5 into Q divided by what? Divided by 4 pi epsilon naught. So now here 1.5 ones and here 1.5 tens. So therefore I can write Q by 4 pi epsilon naught here. Q by 4 pi epsilon naught is equal to 10. Okay, Q by 4 pi epsilon naught is equal to what? Is equal to 10. So this is what I got here. Now I can substitute this here. I can substitute this either in equation 1 or in equation 2. Yes or no? I can substitute this Q by 4 pi epsilon naught value in place of what? In equation 1 or in equation 2. So then what I am going to get here? So let us take equation 1 here. So now VA is nothing but what? VA is nothing but what? VA is nothing but 15 volts. So that is equal to Q by 4 pi epsilon naught. So VA they have given 15 volts. Q by 4 pi epsilon just now we have calculated, that is 10. So 10 by 2. So 15 is equal to, you are having 10 divided by what? 2 plus what? Plus Vk. So 2 ones and here 2 5s. So therefore Vk is equal to what here? Vk is equal to 15 minus 5, that is 10. Okay. So that means the value of the potential at reference point, or I can say the reference potential here in this case, what we got here? We got it as 10 volts. Okay. Now you can determine the potential at what? The potential at point C. The potential at point C. So what is the potential at point C here? What is the potential at point C? Tell me. Okay, so potential at point C. So we have to measure the potential at any point with respect to the given reference point, and the given reference point is K. So VCK. So is equal to what? Is equal to Q by what? Q by 4 pi epsilon naught. So the potential at C due to this point charge Q, the potential at C due to this point charge Q is nothing but what? Q by 4 pi epsilon naught into what? Into the distance from here to here, that is 1. Okay. So Q by 4 pi epsilon naught into 1. Now you want the potential at C, so that is Vc minus Vk is equal to what? Is equal to Q by 4 pi epsilon naught into 1 here. So what is this value here? Q by 4 pi epsilon naught value is 10. Yes or no? Okay. So Vc is equal to 10 plus what? 10 plus Vk, and we have determined Vk is also equal to what? Vk is also equal to 10. Okay, so therefore in this case, therefore the potential at C is equal to what here? Is equal to 20 volts. So therefore the potential at C is how much here? Is how much? Is equal to what? Is equal to 20 volts. Okay, so what do you mean by potential at C is equal to 20 volts? So that means there is a increment of 10 volts as you move from reference point K to what? As you move from reference point K to reference point C. So as you move from reference point K to C, you have gained a potential of what? You have gained a potential of 10 volts. Yes or no? Yeah? Understood? Okay. So with respect to this reference here, with respect to this reference, how much you have gained? You have gained 10 volts. Okay. So the total potential at C is nothing but what? Is nothing but 20 volts. 20 volts. Understood? Okay. Already 10 volts is present at the reference point. So how much you have gained in moving from reference point to point C? How much you have gained? You have gained is 10 volts. So the overall potential at C is nothing but what? Is nothing but 20 volts. Okay. So in general, what we are doing here, we have considered, in general, we have considered the reference point as infinity, and at infinity we have considered the potential as 0. So that's why we got, if we consider it as infinity, then V infinity will be 0. Then in that case, we would have got Vc is equal to what? Vc is equal to 10 volts. Right. Okay. So I hope these points are crystal clear here. Right. Okay. Okay. Okay, yeah, right. Okay, so next another note here. Write down your note here. Write down your note. So all this will comes under special case here. Special cases. Okay. So write down your note here. So what is that note means? See here. The potential at infinity. So in generally we are considering the potential at infinity as what? Infinity as 0. Yes or no? Okay. So here write down this note here. Write down this note. So all these points will comes under special cases here. So the potential at infinity, the potential at infinity is not defined. Is not defined for infinite charge distributions, for infinite charge distributions. So this is very, very important here. This is very, very important. Okay. So what I am saying here, the potential at infinity is not defined for infinite charge distributions. That means if you consider infinite line charge here, if you consider infinite line charge, or if you consider infinite sheet charge. Understood? So for this type of infinite charge distributions, the potential at infinity is not defined. See, in general, for any other charge distribution, what we have considered here, we have considered that the potential at infinity as what? Infinity as 0. But if you consider the charge distributions, infinite charge distributions like infinite line charge or infinite sheet charge, so for that type of infinite charge distributions, the potential at infinity is not defined. Understood? Okay. So that means in this case you have to choose the reference point or the reference potential other than what? Other than infinity, because at infinity the potential is not defined. So you cannot choose the reference point as infinity. So in this case compulsory you have to choose the reference point other than what? Other than infinity. Understood? Okay. So here hence in this case Hence in this case the potential at any point, hence in this case the potential at any point is defined with respect to some other reference point, let us say that is k, some other reference point k. So where k is not equal to what? Where k is not equal to infinity. Understood? Okay. So this point is very important here. So the potential at infinity is not defined for what? For infinite charge distributions. So hence in this case the potential at any point is defined with respect to what? With respect to some other reference point k, where k is not equal to what? Where k is not equal to infinity. Right? Okay. Okay, yeah. So now here see, for example, I am considering okay, for example, if I consider an infinite line charge here, okay, I am considering infinite line charge. Now you want to determine the potential due to this line charge at some point A. So let us say the normal distance of this point from the line charge is rho 1. Okay, so now in general we know that the potential at any point will define with respect to what? With respect to infinity. So let us assume we are measuring the potential at A with respect to infinity. Let us consider here. So this is equal to what? This is equal to integral A to infinity E into what? E into d rho. Yes or no? Here the variable is nothing but what? Here the variable is nothing but rho. Okay, so E into d rho here. So what you are going to get? Integral E, electric field due to an infinite line charge. We know the electric field due to an infinite line charge, that is nothing but what? Rho L by 2 pi epsilon into what? Epsilon into rho d rho. Okay, so here rho L by 2 pi epsilon is constant with respect to integration, so you can take it out of the integration, so you will get rho L by 2 pi epsilon. Okay, so integral what? Integral 1 by rho d rho A to infinity. Okay, where A is nothing but what here? This point is at a distance of what? Rho 1. So in place of A I can write simply rho 1 here. Okay, so in place of A I can write simply rho 1. Right? Okay, so now here I can write this as rho L by 2 pi epsilon. So now integral 1 by rho is nothing but what? Is nothing but ln of rho. Its range is from what? Rho 1 to infinity. So ln of infinity is not defined here. Yes or no? We cannot define. Understood? Okay, so you cannot, so here the reference point you should not take it as infinity. Yes or no? So here this is not what? This is not defined. Right? Okay, what you are going to get? Ln of infinity minus ln of rho 1. So ln of infinity is not defined. Okay, or you will get ln of infinity is not defined. So you should not consider here in this case the reference point as what? The reference point as infinity. So that's what I have told here. The reference point, that means the potential at infinity is not defined due to what? Due to infinite charge distributions. So you are not going to get some finite result here. Understood? Okay, so this is wrong here. So that's why we have to consider what? We have to consider always the potential. If you consider infinite charge distribution, then due to that infinite charge distribution you have to consider some reference point here. So the potential at A, if I say with respect to what? With respect to B. Understood? Okay, so that is B is at a distance rho 2. Let us say B here I am considering as reference point. Now I can determine the potential at B with respect to what? With respect to A, or I can determine the potential at A with respect to what? With respect to B. Understood? Okay, so suppose now if I want to determine the potential at A here, I want to determine the potential at A. So now I can determine the potential at A by taking the reference point as what? By taking the reference point as B. Understood? So that means here VAB. So instead of taking VA infinity, now I am considering the reference point as what? B. So I can take VAB, which is equal to what? Which is equal to integral A to B E into what? E into D rho. So E is nothing but what? E is nothing but rho L by 2 pi epsilon rho D rho. Here point A is at a distance rho 1, point B is at a distance rho 2. Right? Okay, so if you do this, what you are going to get? Rho L by 2 pi epsilon 1 by rho D rho is nothing but what? Ln of rho. Its range is from rho 1 to rho 2. So you can write rho L by 2 pi epsilon into what? Ln of rho 2 minus ln of rho 1. So that I can write it as what? Ln of rho 2 by rho 1. Ln of rho 2 by rho 1. So this is the potential at A with respect to what? With respect to some other reference point B. Okay, but that reference point should not be what? Should not be infinity. You should not take the infinity as reference point if whenever you are having what? Whenever you are having infinite charge distributions. Right? Okay. Okay, yeah. So that's what you are going to get, the potential at A with respect to B. So if you want the potential at A, so then that is equal to what? That is equal to rho L by 2 pi epsilon into ln of what? Ln of rho 2 by rho 1 plus what? Plus VP. Okay. So they will give some reference potential value, maybe 5 volts, 6 volts or 10 volts or something like that. Then you can determine the potential at A. Understood? Okay, so here the potential at A is measured with respect to some reference point B, right? Okay, but you cannot measure the potential at A with respect to infinity in case of what? In case of infinite charge distributions. So in case of infinite charge distributions, the potential at infinity is not defined. That's why you should not take the reference point as infinity whenever you are dealing with infinite charge distributions, right? Okay, so I hope this point is crystal clear here. I hope this point is crystal clear. Okay. Okay, here. Now I will take another example here. I will take another example. Okay, so let us consider an infinite sheet charge here. Let us consider an infinite sheet charge. Let us consider an infinite sheet charge. Let us say the charge density is rho s. The charge density is rho s. Okay. Now you want to determine the potential at A here. Let us say you want to determine the potential at A. So here also the potential at A cannot be defined with respect to what? With respect to infinity. Yes or no? Okay. So here this is nothing but what? This is nothing but infinite sheet charge. This is nothing but infinite sheet charge. So which is having a charge density of rho s coulomb per meter square. Understood? Okay. So here also, if you try to determine VA infinity, so you are going to get what? You are going to get infinite value here, infinite value. Okay. So at infinity you are getting the potential as infinite, which is meaningless here, which is meaningless. So in general the potential at infinity is not what? Is not defined. Okay, so in this case we have to consider the reference point as what? As some other point other than infinity. You have to consider the reference point other than infinity. Understood? Now let us consider the distance from here to here is z1. Okay, now I am considering another point here. I am considering another point B. So this point I am considering as reference point. You can choose any point as reference here. It doesn't matter. Okay, so let us say the distance from the normal distance from the sheet charge to this point is Z2. Okay, so now here, if you want to determine the potential at A with respect to, you have to determine the potential at A with respect to what? With respect to the reference point B. So that is VAB. So that is equal to what? That is equal to integral A to B. Now let us consider this infinite sheet charge is Z is equal to constant plane, and this axis will become what here? This axis will become Z axis. Yes or no? Okay, so if you consider this as z equal to constant plane, and if you draw a normal line to z equal to constant plane, it is going to point along what? Z axis. So I am considering this axis as what here? Z axis, right? Okay, so VAB is equal to integral A to B E into what? The variable is along z, so that is E into dz, so that is equal to what? Integral. So point A is at a distance z1 and point B is at a distance z2. So you have to integrate from z1 to z2. So electric field due to an infinite sheet charge is how much here? Is nothing but what? Rho s by 2 epsilon. Rho s by 2 epsilon dz. Yes or no? So this is the electric field. We have already studied here. The electric field due to an infinite sheet charge is rho s by 2 epsilon. So this is equal to what? This is equal to rho s by 2 epsilon into what? Integral dz. Integral dz is z. So its range is from z1 to what? Z1 to z2, where z1 and z2 are the normal distances from the infinite sheet charge. Okay, remember that point here. Okay, so here what you are going to get? Rho s by 2 epsilon into what? Into z2 minus z1 volts. Okay, so where z2 and z1 are the normal distances from the infinite sheet charge. Understood? Okay, so this is the potential at A with respect to what? With respect to B. Okay, so if you want the potential at A, so then you can write it as rho s by 2 epsilon into what? Into z2 minus z1 plus what? Plus VB. So this is the reference point we have chosen. Okay, so they may give some value of potential at B and they may ask you to determine the potential at A. Understood? Okay. Okay. So I hope these special cases are crystal clear here. Is this clear here? Tell me here. Is this clear? Tell me here. Parasmoon. I think those who are attending the regular classes, okay, so they will understand all these things clearly. Okay, so okay, so is this clear here? Tell me, is this clear? Okay. Okay, yeah. So now I'll just take one problem here, which is very simple. Okay, so you have to tell me the answer for this question here. You have to tell me the answer for this question. Rahul Thakur. Okay, Alok Kumar. Very good here. Very good. Okay. See, in generally in GATE and IES questions, mostly in IES questions also, generally sometimes they are not mentioning all these things here, like they are not mentioning you have to consider the reference point other than infinity, like that. Okay, exactly speaking, they have to mention each and everything here, then only that question will be complete. Okay, but we cannot ask any questions to the examiner, na? Okay. Okay, fine. But whereas if you consider IIT JEE questions or physics questions, so there they are giving the questions each and everything here, each and everything they will give. That means complete information will be present. There will be no confusion, right? Okay. But in IES questions and in GATE questions, sometimes they are not mentioning all these things, right? Okay. It is unfortunate here. Okay. Right. Okay. See here. So see this problem here. So what they have given? The electric potential at the surface of an infinite plane of charge is 100 volts. So the electric potential at the surface of an infinite plane of charge is 100 volts. If the charge density of the charge on the infinite plane is rho s is equal to 1 nanocoulomb per meter square, the electric potential at a distance of 1 meter, from the infinite plane is, okay. So here we know already that due to an infinite sheet charge, the potential at infinity is not defined. So you have to consider some point as reference point other than what? Other than infinity. Understood? Okay, so remember that point here. So they are asking to determine the electric potential, they are asking that the electric potential at the surface of an infinite plane charge is 100 volts. So you are having an infinite plane charge here, you are having infinite plane charge. So you can so those who have understood here, those who have understood previously whatever I have discussed, okay, so you can do it on your own here, you try to solve this problem on your own, okay, so later you can refer the answer. Understood? Okay, so meanwhile I'll try to solve the problem, okay, so meanwhile you try to solve the problem on your own here, right? Okay, so I am considering they have not given any z equal to constant plane or x equal to constant plane or y equal to constant plane, they have not mentioned anything, so I'll just simply consider this as what? This as some z is equal to constant plane, and here the charge density is rho s. Okay, just I have considered here. Okay, you can assume anything, y equal to constant or z equal to constant or x equal to constant plane, whatever you want you can assume. Okay, because it represents what? It represents an infinite sheet charge, that's it. Okay, okay here. So the charge density is rho s. So rho s is equal to what? Rho s is equal to 1 nanocoulomb per meter square. Okay, next one more thing, what they have given here, what they have given, the electric potential at the surface of an infinite plane is 100 volts. So that means on the surface of this infinite sheet charge, on the surface of this infinite sheet charge, they have given the potential as what? The potential as 100 volts. So let us consider a point B on the infinite sheet charge, and at this point B on the surface of sheet charge, they have given as what here? They have given as potential as 100 volts. So at point B the potential is what? 100 volts. Okay, now what they are asking, to determine the electric potential at a distance of 1 meter from the infinite plane. So if you move a 1 meter distance here, 1 meter from the infinite plane, so let us consider this point as what? This point as A. So you have to determine the potential at A, you have to determine the potential at A with respect to what? Due to this infinite sheet charge, due to this infinite sheet charge. Okay, so try to solve this problem on your own here. So before I get the answer, okay, you have to give your answer here, right? Okay, so I hope at least those persons who are attending regularly, so I am hoping the correct answer from you here, right? Okay, so give some answer here, whether it is correct or wrong, it doesn't matter, just give me some answer. So you want to determine the potential at A. Okay, now here in this case you should not consider the reference point as infinity. Understood? Okay, okay, so but they have given what? They have given the potential on the surface of what? On the surface of sheet charge as 100 volts. So I am considering some point on the sheet charge, so the potential on the sheet charge is nothing but what? Is nothing but 100 volts. So that's what they have given. So this point I am considering as B. So at this point B, 100 volts I know. Now I want to determine the potential at A. Okay, okay, yeah. So now I can consider the reference point as what here? Now here I can consider the reference point as what? The reference point as B, because I know the potential at this point. Understood? Okay, so with respect to this reference point, I can determine the potential at A. You can take any point as reference here, but you don't know, suppose if I take some reference point here, C, but I don't know the potential at C. Understood? Okay, so if I know the potential at that reference point, then I can determine with respect to that reference potential, I can determine the potential at any other point, right? Okay, yeah. So just follow the procedure here, just follow the procedure. Okay, so now here I am determining the potential at A with respect to what? With respect to some other reference point. Since I don't know the potential at any other point in space, I know the potential only at this point, which is present on the surface of the sheet charge. So at this point 100 volts. So I am considering the reference point as what here? The reference point as B. Okay, so the potential at A with respect to what? With respect to B. The potential at A with respect to B. Okay, so that is equal to what here? That is equal to, just now we have determined here, yes or no? So what is the potential due to an infinite sheet charge here? Rho s by 2 epsilon, rho s by 2 epsilon into what? Wait here, wait. Okay, wait. Okay, so VAB is equal to what? VAB is equal to integral what? Integral A to B, integral A to B E dz. So this I am considering as z axis here. This I am considering as z axis, right? Okay, yeah. Okay, so this A is at a distance of what here? 1 meter. So this is equal to integral 1 to B. So B is exactly on the surface of what? Exactly on the surface of what? Infinite sheet charge. Understood? So that means what is the normal distance from the infinite sheet charge to B here? Is nothing but what? Is nothing but 0 or not? Yes or no? Because the point B is also lying on what? Lying on the sheet charge, and hence the normal distance from the sheet charge to B will be what? Will be 0. So B I can replace with what? I can replace with 0. So electric field is nothing but what? Rho s by 2 epsilon d z. Right? Okay. So therefore VAB is equal to what? Rho s by 2 epsilon into what? Into z. Its range is from 1 to 0. Okay, so this is equal to what here? Rho s by 2 epsilon into 0 minus 1. So you will get minus rho s by 2 epsilon. So this is VA minus what? VA minus VB. So I want the potential at A here. So therefore potential at A, the potential at A is equal to what? Minus rho s by 2 epsilon plus what? Plus VB. So since they have not mentioned anything about the medium, I am considering epsilon as what? Epsilon is equal to what? Epsilon is equal to epsilon naught. So I am considering epsilon as epsilon naught. Okay, now just substitute all the values here. Rho s, how much they have given here? 1 nanocoulomb per meter square. Yes or no? So that is 1 into 10 power minus 9 divided by what? Divided by 2 into epsilon naught value is 1 by 36 pi into what? Into 10 to the power of minus 9. Right? Plus what is the reference potential they have given? The potential at B is how much here? 100 volts. Is nothing but 100 volts. Okay, so therefore potential at A. Right? Okay, yeah. See, always follow this one here. Always solve the problem like this. Right? Okay. Now what you are going to get here? Here 10 power minus 9, here 10 power minus 9 will get cancelled. Here 2 ones, and here you will get 18 pi. Okay, so therefore you will get minus 18 pi plus what? Plus 100. Okay, so what is 18 pi here? 18 pi is nothing but what? 18 pi is nothing but 18 into 3.14. So if you do this, what you are going to get? 72, 25, 54, 56, right? Okay, 56.52. So that is minus 56.52 plus 100. Okay, so how much you will get here? 100 minus 56.52. So you will get 43.48. Yes or no? So you will get 43.48 volts. So this is the potential. This is the potential at A with respect to what? With respect to B. Yes or no? Okay. Yeah. So the potential at A is equal to what? Is equal to 43.48 volts. Okay. So anybody got this result here? Anybody got this result? Tell me here. Alok Kumar, Rahul Thakur, Paras Moon. Tell me. Anybody got this answer? See, always you have to write, you want to determine the potential at A with reference to B. So you have to write VAB. So that is equal to integral A to B E into dz. Understood? Okay. Yeah. Maybe you have done this mistake here. You would have written VAB is equal to what? Is equal to, you would have written rho s by 2 epsilon into, you would have written 1 meter minus 0. Understood? In this case you will get what? You will get wrong answer. It is not 1 minus 0. It is what? 0 minus what? 0 minus 1. Right? Okay. Right. So in the previous case, how we have defined, you check the formula here, what we got. See, we have considered some point B here and some point A here. So A is at a distance Z2 and okay, wait, we have considered previously, we have considered this as point A and this as point B, yes or no? Okay, so the distance from here to here is Z1 we have considered, and from here to here we got Z2, yes or no? Okay, so we want to determine the potential at A with reference to what? With reference to B. Understood? So in this case what we got? We got integral Z1 to Z2 E dz. So here we got rho s by 2 epsilon into what? Into Z2 minus what? Z2 minus Z1. Understood? Okay, so here you got Z2 is greater than Z1, so you got what? Here positive value. But here you want to determine the potential at A, with respect to what? With respect to B. Understood? Previously B is present here, now B is present to the left of what? To the left of point A, so that's why you are getting minus. So without any confusion, always follow this one here. Without any confusion, always follow this one. So you are going to get the correct answer, right? Alok Kumar, repeat it one more time, sir. Rahul Thakur, where, sir? See, here see, you must be clear which one you are taking as reference point and which one you are with respect to that reference where you want to determine the potential. So here in this case what I have told, I have taken the reference point here, I have taken the reference point as B. I have taken the reference point as B and I want to determine the potential at A. Understood? So that means I have to write the potential at A with respect to reference point B. Understood? So in this case VAB is equal to what? Integral A to B. Integral A to B. Okay, so A is at a distance Z1 and B is at a distance what? B is at a distance Z2. Understood? So integral E dz. So here just substitute rho s by 2 epsilon dz. If you do this integration, you are getting the potential at VAB is equal to what? Rho s by 2 epsilon into Z2 minus Z1. If you want the potential at A, that is equal to what? Rho s by 2 epsilon into Z2 minus Z1 plus VB. Understood? Okay, is this clear? Is this clear? Yes or no? Okay, now if suppose they have given that, consider A as what? If suppose they have given that, consider A as what? A as reference point and try to determine the potential at B. So in this case what you have to do? You have to consider the you have to determine the potential at what? Potential at B with respect to what? With respect to reference point A. Understood? So always you have to write here in the subscript, always the first one you have to write where you want to determine the potential, and the second one is with respect to which reference point. So that's what you have to write here. Understood? Yes or no here? Okay, so based on this you have to determine, right? Is it clear here? Tell me here. Is this point clear? See, previously, yes or no here? Is this point clear? Tell me. So whenever you are writing the subscript here, how you are going to write? The potential at some point with respect to what? With respect to reference. Yes or no? So second one, you are going to write what? We are going to consider it as what? This is reference point, and this is nothing but what? This is nothing but the potential at which point you want to determine. This is how you are writing or not? Yes or no? Okay. Okay. Right. So here, so in this problem they are asking to determine the potential at A. They are asking to determine the potential at A. They are not saying anything about the reference point. They are asking to determine the potential at A. Okay, but since we know the potential at B, since they have given the potential on the surface as 100 volts, so I have considered some point on the surface. So at that point I am considering the potential is what? 100 volts. Now here I know this potential here. I know this potential, and hence I am considering this as what? I am considering this as what? This as reference point. Right, this as reference point, because I want to determine the potential at A with respect to some other reference point. So that reference point I have taken here as B, because I know the potential at this reference point. Understood? So if I know this one, then I can easily determine the potential at A. Yes or no here? Okay, so here, so that's why don't blindly follow the formula. Understood? So always you must understand the procedure and concept. That is very, very important. Okay, so if you would have written just simply in this manner, rho s by 2 epsilon into z2 minus z1, okay, so you would have taken z2 as 1 meter and z1 as 0, then you would get VAB as some positive value, which is wrong. Yes or no? Understood? Okay, so that's why I always follow the procedure and concept. That is very, very important. Okay, so that's why I have given this problem here. Right? Okay, so you want to determine the potential at A with respect to B. So then write rho s by 2 epsilon integral dz. It is very simple integration. Integral dz is z. That's it. Okay, if you substitute the range, automatically it will take care here. It will take care whether the value is positive or negative. Understood? So if you just follow this procedure, so automatically plus and minus signs will get taken care of. So what I am saying is, don't just blindly follow the formula. Okay, so understand the concept and understand the procedure clearly. Okay, then you won't do any mistake. Right? Okay. So is this problem clear here? Tell me. Is this clear? Right? Yes? Okay, yaar. Okay. Okay, yaar. So these are the special cases here. All this will come under, today whatever I have dealt about the potential, everything will come under what? Will come under this special cases. Special cases. All these are special cases here. Right? Okay. So you must get familiar with these special cases also. Right? Okay. So this is also important here, right? Okay. So note down all these points. Okay. Okay. So with this, I have covered each and everything here, almost each and every concept that is present in electrostatic potential energy and electrostatic potential. Okay, so if in any exam, if any question comes in this topic, okay, you should not do any mistakes here. You should not do any mistakes. Okay, so you have to practice more and more problems, revise as many times as possible, so then you will get perfection. Okay, so then doing mistakes, the chances of doing mistakes will be very, very less. Right? Okay. Okay. So next year, we are going to start magnetostatics. Okay, so next we are going to start with magnetostatics. Right? Okay. So here I will start this magnetostatics with a statement. Okay, so what is that statement? See here. So magnetism is caused by moving charges and is also felt by only moving charges. Okay, so this statement is very important here. Okay, so what I am saying here, see here, magnetism is caused by what? Is caused by moving charges and is also felt by what? And is also felt by moving charges. So what do you mean by this statement? Magnetism is caused by moving charges and is also felt by only moving charges. So what do you mean by this statement? See here, so whenever you place a charge, here, okay, so let us say this charge is stationary here. Let us say this charge is stationary, it is not moving. Understood? So whenever you place a stationary charge at this location, what it is going to do here? It is going to set up some electric field. It is not going to produce any what? It is not going to produce any magnetic field. Yes or no? So that means a stationary charge cannot produce any magnetic field. Yes or no? Okay, so then which type of charge will produce magnetic field? If suppose the charge moves with uniform velocity here, let us assume the charge is moving with uniform velocity. So if the charge is moving with uniform velocity, I can consider it as what? I can consider it as current. Yes or no? If the charge is moving with uniform velocity, it is going to produce what? It is going to produce a steady current. Yes or no? Okay, so if charge is moving, with uniform velocity, if a charge is moving with uniform velocity, okay, so it is going to produce what? It is going to produce steady current. It is going to produce steady current. Yes or no? So whenever you are having a steady current, it is going to produce what? It is going to produce a steady magnetic field. Yes or no? So we know that the source of magnetic field is nothing but what? Current, and the source of electric field is nothing but what? Charge. Understood? So the current is also nothing but what? From where we are getting current? The current is also we are getting from charge only, but here it depends upon what? It depends upon the state of charge. That means whether it is stationary or it is moving. So if it is stationary, it is going to produce only electric field. If it is moving with uniform velocity, then it is going to produce what? A steady current. And if you are having steady current, we know that it is going to produce what? It is going to produce magnetic field. Understood? Okay, so it is going to produce what? It is going to produce a steady magnetic field, or generally I will represent with B field here. Okay, so steady B field, I can write steady B field, right? Okay, so that means a stationary charge cannot produce what? Cannot produce any magnetic field, whereas a moving charge can produce what? Finally it is producing what? It can produce magnetic field. Understood? So that's what this statement mean here. So what I am saying here, magnetism is caused by only what? Is caused by moving charges. Magnetism cannot be caused by stationary charge. Understood? Okay, so this is completed. Next, what I am saying, and is also felt by only moving charges. And is also felt by means what here? And the magnetism is also felt by what? Is also felt by moving charges. That's what it means. Okay, see, understand this statement clearly here. Magnetism is caused by moving charges and is also felt by. That means the magnetism is also felt by only what? Only moving charges. Understood? Okay, so in order to understand this one, see here, if I consider a magnet, let us say this is north pole and this is south pole. Okay, we know that always the magnetic field lines will start from north pole and end at what? And end at south pole. So let us say this is B field. Okay, let us say this is B field, right? Okay, now it is observed that whenever you place a stationary charger, whenever you place a stationary charge, it is observed that it is not experiencing any force here. Okay, so if you place a stationary charge in a magnetic field, then it is observed that this stationary charge is not experiencing any magnetic force, So that means a stationary charge cannot feel the magnetic force, Yes or no? Okay. Now here in place of charger, whenever we have placed a current carrying wire here, let us say the current is flowing in upward direction or downward direction, whatever you want you can take. Okay, let us assume the current is flowing in upward direction. Understood? So if the current is flowing means what here? The current is flowing means the charge carriers are moving inside the conducting material with uniform velocity in upward direction. Yes or no? So that means I can consider this current as what? The charge carriers that are moving with uniform velocity will result in current. Yes or no? Okay, so that means what here? That means the charge carriers are moving. Yes or no? The charge carriers are moving inside this conducting material. So whenever the charge carrier is moving inside the conducting material, it is observed that a moving charge is experiencing what? Is experiencing a magnetic force. Or I can simply say, whenever you place a current carrying wire, it is observed that this current carrying wire is experiencing what? Is experiencing a force. Is experiencing a magnetic force. It is experiencing a magnetic force. Okay, so what do you have understood by this here? So a current carrying wire is experiencing a magnetic force means what? Inside the current carrying wire, what is present? The charge carriers are moving with uniform velocity. Yes or no? So that means whenever the charge carriers are moving with uniform velocity, then it is going to experience what? It is going to experience a force. Understood? Okay, so that means magnetism cannot be felt by a stationary charge, but the magnetism will be felt by what? Will be felt by only moving charges. Understood? Okay, so that means what here? The magnetism is caused by only moving charges, and this magnetism is also felt by what? Is also felt by only moving charges. A stationary charge cannot produce magnetic field, as well as a stationary charge cannot experience any magnetic force. Understood? Okay, so these points are very, very important here. Okay, so this statement is very important. So magnetism is caused by only moving charges and is also felt by only moving charges, right? Okay, so I hope this statement is crystal clear. Yes or no here? Is this statement clear here? Tell me. Okay. Okay, yeah. So so I have told that a moving charge in a magnetic field is going to experience what? A moving charge in a magnetic field is going to experience a magnetic force. Okay, so what is that force? How much force it is going to experience? So that is given by Lorentz force equation. That is given by what here? Lorentz force equation. Okay, so the magnetic force experienced by a moving charge. See, moving charge means it is moving with uniform velocity. That's what you have to understood. Okay, the magnetic force experienced by a moving charge in B field is given by Lorentz force equation. Is given by what here? Is given by Lorentz force equation for B field. Lorentz force equation for B field. Okay, so what is that Lorentz force equation for B field? So see here. So the Lorentz force equation for B field is nothing but F is equal to what? F is equal to Q into V bar cross what? V bar cross B bar. So this is called as Lorentz force equation for B field here. This is called as Lorentz force equation for B field. Understood? Okay. So that means whenever you are having a charge, moving with velocity v in B field B, then it is going to experience a force F. Understood? So this force F is nothing but magnetic force. Okay. So in general, I can represent this with F subscript B, or simply I will represent with F bar. Understood? Okay. Okay. So in order to make you understand each and everything clearly, so I am representing here subscript with BR. Understood? Okay. Generally in books they won't represent all these subscripts and all. They will simply represent with F bar. So you should not confuse with that. Right? Okay. So this is the expression for Lorentz force equation due to magnetic field. So that means if you observe this equation here, see, if the velocity of the charge is equal to 0, then the magnetic force is also equal to what? Is also equal to 0. So that means if the charge is stationary, then its velocity will be 0, then the force will also be what? Force will also be 0. So from here also we can say that a stationary charge cannot experience any what? Cannot experience any magnetic force. Understood? So whenever a charge is moving with having some velocity v in magnetic field B, then only it is going to experience some force. Okay. So a moving charge in B field is going to experience force. A stationary charge in B field cannot experience any force. Okay. So that's what you have to understand. Okay. Okay. So now you may ask that, sir, you have told Lorentz force equation for B field. Is there any Lorentz force equation for electric field? Yes, here. So Lorentz force equation for electric field, Lorentz force equation. Okay. Lorentz force equation for electric field. This already you know here, that is nothing but what? F is equal to what? F is equal to E into what? E into Q. So F bar is equal to E bar into what? E bar into Q. E bar into Q. So this is called as Lorentz force equation for electric field. You know this one? Yes or no? Okay. Now now if you observe from this equation, what you can conclude here? If suppose if you are having electric field, in this direction, let us assume this is electric field here. Right. Now suppose you are having a charge Q. Right. So whenever you place a charge Q in electric field, it is going to experience the force in which direction? If Q is positive here, Q is positive charge. Understood? So or I can represent plus Q. Simply I am representing with plus Q. So you have to understand that it is positive charge. So whenever I place a positive charge in electric field, it is going to experience the force in which direction? Along the direction of electric field or not? Yes or no? So it is going to experience the force along the direction of what? Along the direction of electric field. So this is the direction of what? This is the direction of electrical force. So here this is electrical force here. So that means if Q is positive, then the direction of electrical force and electric field both are what? Both are in the same direction. Right? Okay. Okay. Now suppose here if I write if I place negative charge here, okay. So if I place negative charge minus Q, okay, in the electric field, so then in which direction it is going to experience the force here? Minus Q. So it is going to experience the force against what? Against the electric field direction or not? Yes or no here? Yes or no? So minus Q is going to experience the force. In this direction. So this is the electrical force. Yes or no? Plus Q is going to experience the force along the direction of what? Along the direction of electric field. Whereas minus Q is going to experience the force against the direction of what? Against the direction of electric field. Understood? So what do you mean by that? If you just simply leave plus Q charge here in the field, in the electric field, then it is going to move along the direction of electric field. Understood? Or if you simply leave a minus Q charge in electric field, then it is going to move what? Then it is going to move against what? Against the electric field. So if you put here in place of Q, if you put minus Q, Okay, so in place of Q, if you put minus Q, then you are going to get what? The direction of electrical force will be opposite to what? Will be opposite to the direction of electric field. So that means a negative charge is going to move against the field and a positive charge is going to move along the field. Understood? So from here, what you can conclude here is the electrical force here, the electrical force direction will be either along what? Will be either along the direction of the field, or it will be what? It will be against or opposite to what? Opposite to the direction of the field. So only two chances for electric force here, for electrical force. So the direction of electrical force will be same as what? Will be same as the direction of electric field if the charge is positive. Otherwise, the direction of electric field force is opposite to what? Is opposite to the direction of electric field if the charge is what? If the charge is negative. Right? Understood? Okay. So I hope this point is clear. I hope this point is clear. Right? Okay. Okay. So just 1 minute here. Just 1 minute. Okay. Okay. Just give me 1 minute break here. So within 1 minute I will come back. Just 1 minute break. Right? Okay. 1 minute here. So some emergency call. Okay. 1 minute here. 1 minute I will come. Okay. Okay. So sorry for the interruption because it is a somewhat emergency call, so that's why I have to attend that. Okay. Okay, yeah. Fine. Here what we have seen here, the electrical force is either along the direction of what? Along the direction of electric field, or it is opposite to the direction of electric field, depending upon what? Depending upon this charge. Understood? Okay. Okay, yeah. Now here coming to this one here, magnetic field force, coming to magnetic field force. Okay, here the field direction, and force direction may be in the same direction or opposite to one another. Okay, these are the chances, that's it. Understood? But here, when coming to here, this is the magnetic force, okay. So this is the magnetic field, or I can say magnetic flux density here. In generally, B is called as magnetic flux density. So every time I don't call it as magnetic flux density like that. Okay, so I will simply call it as magnetic field. You have to understand here. Understood? But I will represent here. I will represent whenever I am saying magnetic field, either I will represent with B or I will represent with H. Okay, H is called as, in general it is called as magnetic field intensity, and B is called as magnetic flux density, Okay, we will see the differences and all those things later. Okay, but whenever I am saying B or H, I will simply represent with magnetic field. I will simply call it as magnetic field. So don't confuse with this here. Okay, but I will that means I will write here whether I am saying about B field or H field. I will write that, but both I am going to call it as simply magnetic field. Understood? I don't use every time magnetic flux density, magnetic field intensity like that. Okay, so so please understand that, right? So even though I am saying it as magnetic field, I will represent that with a symbol, na? So then you according to that symbol you have to understand, right? Okay, but in problems, while giving the problems, I will give each and everything in detail, don't worry. Okay, yeah. So here what is the here this is the force direction here, this is the force direction, and this is field. So this is B field, right? This is B field, and this is magnetic force, this is magnetic force. Yes or no? Okay, now the direction of magnetic field force and the direction of field, how they are here? Tell me how they are. Will they are along the same direction or they are not along the same direction? First one, tell me whether both are pointing in the same direction or both are not pointing in the same direction. So just tell me the answer here. Tell me. Here in electric field case, the electric field direction and the electrical force direction both will be in the same if charge is positive, if charge is negative, both are opposite. That's we know. Okay. Here what I am asking here is, here also I am considering the force and field. Understood? Now tell me whether the direction of field force and the direction of field both are in the same direction or opposite direction, or we cannot say that. Tell me here. Depend upon the movement of direction of charge perpendicular to each other. Very good, Alok Kumar, very good here. Perpendicular to each other, very good. Okay, see here. See here. So FB is equal to what? FB is equal to what? FB is equal to, let us for example, let us consider velocity is in x direction. Let us assume velocity is in x direction and B field is in y direction. Okay, whenever you get a doubt, you can represent like this here. So let us assume velocity is in x direction and B field is in y direction. Then what is the direction of force here? So x cross what? X cross y. Yes or no? So x cross y is nothing but what? Is nothing but z. So that means the magnetic force will be in which direction? Z direction. Understood? Or you know that whenever you are doing A bar cross B bar here, if you do A bar cross B bar, the resultant vector will be perpendicular to what? Will be perpendicular to both A bar and B bar. Now here F bar is the resultant of what? Resultant of this cross product or not? Yes or no? So that means F bar must be perpendicular to both velocity as well as what? As well as magnetic field. Understood? So this is the first observation we can make. This is the first observation we can make. So what is the observation here? Tell me. So here the magnetic field force and the magnetic field both must be what? Both must be perpendicular to one another. Understood? Okay. But here it may be along the direction of the field or it may be opposite to the direction of field. But here it is always perpendicular to what? Perpendicular to the direction of magnetic field. Right? Okay. So here FB and B field, FB and B field are perpendicular to what? Perpendicular to each other, or perpendicular to each other. Okay. So understood here? Rahul Thakur, understood this point? Yes or no? Okay. Parasmoon, perpendicular, very good. So Rahul Thakur, I hope you have understood this one, right? Okay, yeah. So now okay, are perpendicular to one another. So now I will give you some diagrams here. You have to tell me the resultant force direction, right? Okay. So here I am considering the B field. So here this is the B field here. This is the B field. Here B field is pointing into the board. B field is pointing into the board, right? Okay. Now let us consider this axis as x axis and this axis as y axis and this axis as z axis here, z axis. Okay. So this is B field, this is B field. Now here the B field is pointing into the board. Into the board means which direction here? It is pointing into the board, that is it is pointing in negative z direction. Yes or no? I hope you know this notation here. If you represent into mark and if you encircle the if you enclose this into mark with a circle, it represents the vector is pointing into the board. So if I represent with a dot and if I enclose this dot with a circle, then it represents the vector is pointing out of the board. Yes or no? Okay. Okay. So I hope you know these things. So here the B field is pointing into the board. So that means here B field is pointing into the board. That means B field is in negative Z direction. Now let us consider charge Q. Let us consider charge Q. Okay, so let us say this is plus Q here. Let us say this is plus Q. Let us say this is plus Q. Plus Q. Okay, so let us assume plus Q is moving with velocity V. It is moving with velocity V in X direction. In X direction. Understood? And B field is pointing in negative Z direction. Now tell me in which direction it is going to experience the force at this point. Tell me. Now here plus Q is present. Now it is moving in magnetic field B field with velocity V in this direction. Now in which direction it is going to experience the force at this location? Tell me. Tell me here. So what you will do is always write this one here. So F is equal to what? F is equal to Q into what? Q into V bar cross what? V bar cross B bar. Right. So here velocity is in which direction here? Velocity is in X direction. Yes or no? Velocity is in X direction and B field is in negative Z direction. Negative Z direction. Understood? Okay. So the resultant force will be in which direction? Tell me. See, whenever you are having here you are having X and here you are having minus Z. Okay. What is X cross Z here? Forget about minus sign here. Forget about minus sign. So what is X cross Z? X cross Z is what? Minus Y. Minus Y. Yes or no? So minus of minus will become what? Minus of minus will become plus. So that means the this force will be in which direction? Will be in Y direction. Understood? So that means this plus Q charge is going to experience the force. Is going to experience the force in Y direction. Understood? Yes or no here? Okay. Now see here. So let us say this is 1. Next, if suppose the same thing here, if I consider okay. So now if suppose minus Q charge here, I am considering minus Q charge. Okay, so it is moving with velocity V. It is moving with velocity V in this direction. Always consider the coordinate axis in this manner here. X in this direction, Y in this direction, Z is coming out of the board. Now here minus Q is moving with velocity V in this direction. Understood? Now in this case, in which direction it is going to experience the force here? So F is equal to what? F is equal to, now in this case, minus Q into V. V is in X direction. V X cross B, I have not changed. It is in minus Z direction. So what is the resultant force direction here? Tell me. What is the resultant force direction? X cross Z here. X cross Z will be minus Y. So minus of minus will become plus. And again you are having minus. So in which direction it is going to experience the force? It is going to experience the force in minus Y direction. Minus Y direction. So it is going to experience the force in minus Y direction. Understood? Okay. Okay. Yeah. So next, for this one you have to tell me the answer here. For this one you have to tell me the answer. So this is nothing but B field, right? So this is nothing but B field. Now here B field I have considered it is coming out of the board. That means in positive Z direction. In positive Z direction. Okay. Now if suppose minus Q charge is moving with velocity V. With velocity V in this direction. Now tell me the force direction here. Tell me the force direction. Tell me here. Tell me in this case what is the force direction? Rahul Thakur, Alok Kumar, Paras Moon, tell me here. In which direction it is going to experience the force? in minus y. Rahul Thakur told minus y. Is any other answers here? Alok Kumar, in which direction it is going to experience the force? So F is equal to what? F is equal to minus q into velocity is in negative x direction cross what? Now here B field is in positive z direction, right? Okay. So what is, whenever you are having minus, first neglect that minus here, don't consider that minus, just take x, z. So what is x cross z here? X cross z is nothing but what? Minus y. So minus of minus will become plus, and again here you are having minus. So that means it is in which direction? The resultant force will be in minus y direction, right? Alok Kumar, here I have given now everything. Minus q is moving in this direction, yes or no? That is minus x direction velocity. B field is in positive z direction, minus q. So it is going to experience the force in which direction? Minus y direction, yes or no? So it is going to experience the force in negative y direction, right? Okay. So last one here, last one. Okay. So now you have to tell, everybody has to tell me the answer correctly here for this one. Okay. So let us say minus q is moving with velocity v. So this is B field. In which direction it is going to experience the force? Tell me. Always you have to consider, here I have given the reference axis, yes or no? X axis you have to consider in this direction, y, z. According to this, tell me here, in which direction it is going to experience the force? Minus q. Just to follow the procedure here, you are going to get that. See, why I am giving these things means generally the students will have some confusion whenever you are having a positive charge and whenever you are having negative charge. Okay, so in which direction they are going to experience the force? So this confusion will be present. Okay, so that's why in order to clarify that confusion, I am giving this many examples here. See, based on this Lorentz force equation, we are having an application in EDC, that is nothing but Hall effect here, Hall effect. Okay, so Hall effect is completely based upon this Lorentz force equation. Okay, so if possible in the next class I will tell that application also. Okay, application of this Lorentz force equation, right? So in which direction here? Rahul Thakur has given minus x, Alok Kumar has given plus x. See, still I am getting two different answers here. I think you are familiar with cross product or not? Yes or no? You know ax cap cross ay cap is az cap. You know all these things or not? Okay, I hope so. So what is the force here? Force F is equal to what? I have given minus q, that is minus q. It is moving in downward direction. Downward direction means in which direction here? Negative y direction. Yes or no? And B field is pointing in negative z. Okay, so what I have told here minus, minus into minus will become plus. So y cross z is nothing but what? X, and here you are having minus. So it is going to point, the resultant force direction will be in which direction? Negative x direction, negative x direction. Okay. Alok Kumar, I think you are confused with this cross product, I think so, right? So just practice that here, it is very simple, right? Okay, so the resultant force will be in negative x direction. So that means negative x means it is going to experience the force in negative x direction, right? Is this clear? Tell me here. See, you have to know these things here. Ax cap cross ay cap is equal to az cap. Ay cap cross az cap is equal to ax cap. Az cap cross ax cap is equal to what? Is equal to ay cap. So always follow this one here. Okay, so if you move, if you do ax cap cross ay cap, you will get az cap. If you do ay cap cross az cap, you will get ax cap. If you do az cap cross ax cap, you will get ay cap. If you move in opposite manner, you have to get negative. Okay, so that is, if you do ay cap cross ax cap, you have to get minus az cap. If you do ax cap cross az cap, you have to get minus ay cap. Understood? If you do az cap cross ay cap, you have to get minus ax cap. Right? Okay, so remember this one here. I have told all this right hand rule and everything while dealing with coordinate systems, right? Okay. Yes. So that confusion must be clarified here. So that's why I am giving these examples. Okay. So generally the students is having that confusion. So whenever they are having plus q and minus q, they will get confusion. Understood? So that's why I am giving this, right? Okay. Okay, so I hope now it is clear, right? Alok Kumar, I hope now it is clear, right? Okay, now last one here, last one, see here. So fifth one. So now let us say here B field I am considering in this direction here. B field I am considering in this direction. Okay, so here this is nothing but what? This is nothing but B field. Now B field I am considering in positive x direction. Now let us say I have placed here plus q charge, okay, and here I have placed here minus q charge, right? So it is moving with velocity v here. Let us say minus q is moving with velocity v here. Okay, now what is the force experienced by plus q and minus q here? That means in which direction plus q and minus q are going to experience the force? Tell me. Here B field is pointing along x direction. I have considered the B field in x direction. Now the charge is moving. The charge is moving with velocity in this direction. Plus q is moving in this direction. Minus q is moving in this direction. Okay. So now tell me, or you can consider. Okay. You consider first plus q here. Tell me here. Tell me in which direction it is going to experience the force. Tell me. In which direction it is going to experience the force? Tell me here. In which direction it is going to experience the force? Tell me. What you are thinking here? It is very simple or not? It is 0, yes. So here it is not going to experience any force. Why? F is equal to what? F is equal to q into what? Q into v bar cross b bar. Velocity is in x direction. B field is also in x direction. So both are in x direction means the force it is going to experience is equal to what? Is equal to 0. So that means it continues to move in the same direction. Understood? Whether it is plus q or minus q, it continues to move in the same direction. It is not going to experience any force. Understood? Okay, so the force experienced by a charge, if the velocity of the charge and the B field both are in the same direction, then the force experienced by that charge will be equal to what? Will be equal to 0. So if I take minus q and if I consider the velocity in this direction, here also you are going to get what? You are going to get F is equal to what? F is equal to 0 only. F is equal to 0 only. So here you are going to get velocity in negative x direction, B field is in x direction. So minus ax cap cross ax cap will also be what? Will also be 0. Understood? Okay. Okay. So that means if the charge is moving along the direction of the field, it is not going to experience any force. Right? Okay. Last and final here. Last and final. Okay. Now same here. I am considering B field. So this is B field. Right. Now let us assume the velocity. Let us assume plus q charge here. Let us assume plus q charge is moving with velocity in this direction. Is moving with velocity in this direction. Okay, okay. Then what is the resultant force direction? Tell me. It is moving with velocity in this direction here. So this is x-axis I have given, this is y-axis, and this is z-axis, right? So it is a xy plane, it is xy plane. So let us consider this is x-axis, and let us consider this as what? This as y-axis, right? So now the charge is neither moving along x nor along y. It is moving in some resultant direction like this. So it is neither moving along x nor along y. It is moving in some resultant direction like this here. Okay. Now in this case, in which direction it is going to experience the force? Tell me. In this case, in which direction it is going to experience the force? Tell me. At this point, in which direction this charge is going to experience the force? Now this velocity v is neither along x nor along y. So it can be resolved into two components. One is what? One is along x, another one is along what? Y. Yes or no? So that means this velocity v is going to have two components. One is what? One is along what? One is along x direction, and another one is along what? Another one is along y direction. Understood? Okay. Now tell me here, in which direction it is going to experience the force? Tell me. I have already given the clue also, right? Tell me here. Tell me here, in which direction? Minus z direction. Okay. Alok Kumar, 0 force. Okay, that is previous one, right? Okay. Rahul Thakur is saying negative z direction. So let us check here. Let us check in which direction it is going to experience the force. So F is equal to what? F is equal to Q into what? Q into V bar cross B bar. Now V is having two components, that is Vx Ax cap plus what? Plus Vy Ay cap. Cross what? Cross B bar. B bar is in which direction? B bar is in x direction. B bar is in x direction. Right? Okay. So if you do the cross product between these two, what you are going to get? Ax cap cross Ax cap will be 0. So you are going to get what? Q into Vy into B. Vy into B. Ay cap cross Ax cap is nothing but what? Is nothing but minus Az cap. Minus Az cap. Right? Okay. So that means the resultant force will be in which direction here? Negative z direction. Negative z direction. So that means this plus q charge is going to experience the force in negative z direction. That means into the board here. It is going to experience the force into the board. Into the board. So that means here the force will be in negative z direction. So that is into the board. That is into the board. Understood? Okay. Okay. Very good, Rahul Thakur, very good. Okay. It is in negative z direction. So in this manner, you have to determine what? You have to determine the in which direction that charge is experiencing the force. Understood? See, because of x component, it is not going to experience any force, because the x component of velocity and B field, if both are in the same direction, due to this component, it is not going to experience any force. So it is going to experience the force only due to what? Only due to the y component of velocity. Understood? Okay. So if you do the cross product between y component of velocity and B field, the resultant force direction will be in negative z. So this is going to experience the force in which direction? Negative z direction. Right? Okay. So I hope all these things are crystal clear here. Okay. So if you have understood these things, okay. So tomorrow I will tell you the application of this one here, the application of this Lorentz force. Okay. So we have seen Lorentz force equation for what? For electric field, and also we have seen Lorentz force equation for B field. Understood? Okay. Okay. So based on this Lorentz force equation, we are going to see one application. So I will briefly explain here. I will briefly explain the application of this one. Okay. So that will come under in EDC. So that is a Hall effect. Hall effect. In Hall effect, you are going to use this Lorentz force equation. Understood? Okay. So briefly I will explain within 10 to 15 minutes. Briefly I will explain what is that application. So later we will continue this topic here, our magnetostatics, right? Okay, so I hope each and everything is crystal clear up till now. I hope so, right? So tomorrow we are going to start the session exactly at what? Exactly at 4 p.m. Exactly at 4 p.m. Right? Okay. So with this, I am winding up the session, and tomorrow we will meet exactly at 4 p.m. Right? So if you have any doubts here, do you have any doubts? Everything is crystal clear? Tell me here. If everything is crystal clear, then we will wind up the session. Tell me. Do you have any doubts? Alok Kumar Thakur. Okay. No, very good here. Okay. So I hope everything is crystal clear. So tomorrow exactly at 4 p.m. we are going to start the session, right? Okay. So with this, I am winding up the session. So we'll meet exactly at 4 p.m. tomorrow. So until then, take care. Bye bye.